Ngalakin Khadijan Nyunga Boja.
All right. Ruby's already asked me what happens if she goes over time, so we should probably start on time. So today we have a guest lecture by Ruby Kaur. Ruby is another professional engineer who has been supporting our electrical engineering design units for a number of years now, both in terms of these kinds of lectures as well as a industry facilitator or supervisor. So Ruby has a Masters in Engineering from the University of South Australia, Adelaide, South Australia. And she's a chartered engineer. I'm sure by now most of you should know what that means. And she is a senior telecom and security engineer for Hitachi Rail. Okay, so I'm not going to hang around here much longer. I'm just going to pass it on to Ruby to share her experience with you. Thank you.
Okay.
That goes in the book at least.
Oh dear. Hello. Hello everyone. Today we're going to learn about telecom system design process. Subtitle is an introduction because there's only so much we can fit in this 1 hour. Now, it does say telecom system design process because I'm a telecom engineer and I am confident that this is what we do. But the learning outcomes are very much transferable to other systems as well. So let's begin. Major learning outcomes today. We learn about a system life cycle stages. It will help you with the design unit this semester, next semester, and when you get to work, definitely everything will make sense if you remember a few bits of this. Understanding the data deliverable stages and types. If we have time afterwards, I will show you some of my drawings as well. And the understanding the design review process. If you take lots of notes, just the keywords of what I'm saying, whatever you see here, and then when you get to work, all the dots will connect and things will make much more sense. Engineers, terms and conditions apply. These things, the reason I put those that these are out of scope is because so you don't think what we're learning today is the complete picture, but it's just a subset. These are really useful terms that we actually need to know if we want to know the full picture. So I put those there in case anybody is interested to learn more complete picture, that is. Keywords. Everybody knows what a project is. But okay, so deliverables. What is a deliverable? A project deliverable are the quantifiable goods and or services that must be provided for the completion of a project, which is what? Say, if we are building, say we have a telecoms project connecting two mine sites and with a microwave link. So, is that not loud enough? Okay, all right. So you have microwave links, the towers, dishes, indoor equipment, power supplies, things, these are deliverables. But also there'll be an engineering design, which is an data deliverables, which is where we'll focus today. So the data deliverables are a set of documentation required to demonstrate the delivery of a compliant solution. Drawings, reports, schedules, test procedures, test results, everything. So what is engineering is basically a big chunk of documents. A list of those is called SDDR or SDL. I'll put those there because they're pretty common terms. Next. This is a useful slide. So what we're looking at here is the project stages and the corresponding design stages. Now, I've drawn it like from the point of view of an EPC contractor. EPC, engineering, procurement, construction. So the arrow where it says award and handover, this is from the perspective of us, design engineering in an EPC contracting company. So feed happens before we get the contract. We'll go through those stages in a sec. And handover is when our work is done. Okay, quickly. There's a lot to cover, so I'm going to be a bit fast. But you can probably, I think it's better if you ask questions as I go, only burning questions. And then I'll try to answer in the end as well. I'll stay back if we don't have time. Feed is front-end engineering and design. This is basically a feasibility study. We are planning to build something, but we need to make sure it's technically feasible, if it's going to be worth the investment or not. We need to, let's say Chevron wants to build another LNG plant here in WA. They need to see so many different aspects, not just engineering, environmental, political, and then they need to see how much gas is under there, are we even going to make money? So all of that happens before the award. So this is the feed stage. And for engineers, that design stage is called concept design, as you can see underneath. So feed is done when the company decides, okay, we're going to go ahead with the project. What happens next is a stage called the actual project, which most of my projects were EPC projects. But again, these stages could be broken down based on how that company manages their projects. Again, how the scale of the project, the complexity of the systems. But more or less, these are the stages, and this is what typical design looks like.
It's blocking the screen a little bit for some reason. The Zoom.
Oh, okay.
Recording in progress.
Did we miss the first 5-10 minutes?
Yeah, I don't know why. Yeah, that's right.
Okay. Okay, so award. It's when a contract is awarded. So after the feasibility studies are done, the companies request for tenders from different subcontractors, contractors, and award. We're not going to go in that much detail, but we have the contract now. As engineers, you are a design engineer. What you start with is called preliminary design. We're going to go through what goes in there. I will probably show you some drawings as well in the end. Next stage is after engineering design is approved, procurement, which is just buying of equipment. The next stage is construction, and afterwards it's commissioning, which is testing, just a fancy name for testing. There are various testing stages. We'll also cover those later. And after successful testing, we hand over the system. Afterwards, the companies, they own the network. that's when the next stage, which is the longest stage in a system's life cycle, is O&M, operations and maintenance. So somebody built this room, they hand it over to the uni, now uni is doing the ops and maintenance. Sometimes companies actually hire other companies, some consultants, to do that if they don't have the capability. Now, then many decades down the line, technologies become obsolete, equipment stop being made, you don't have spares, you decommission the system. So this is the whole life cycle of a system. And the design stages, we start with the concept design. Then when we start the project itself, we start with preliminary design, detailed design, and then we do something called IFC, issued for construction, which is essential for building. We cannot just build on any random drawing, has to be IFC. Then after we hand over the issue, we issue something called IAB design, issued as built. Now, we're going to go through all of these in the following slides. You don't read the title. Okay. Title says concept design. Happens pre-award feasibility study. The purpose is to, from engineering side of things, we're only talking engineering, estimate the technical feasibility and investment in terms of time and money, usually done by consulting companies, subject matter experts. So this photo is a few weeks old. That person on the right side next to the tower is my friend Roger. He is a senior telecom engineer, and the photo is taken by the principal engineer. This is on one of the Rio Tinto mine sites. What we're doing is we see on the left side there's a train track. Rio Tinto own their own private rail network. I heard it's the world's biggest privately owned network. So it's old. See, there is a little cabinet, this cabinet. You see the cursor? Yeah. So trains have different types of sensors that send data to the train control system. Train control system actually sends that data to the train, whether track is clear or not. If it's not, then the trains stop. And stopping commercial trains is not a good idea because every second loses you money. And because these trains actually carry iron ore dug from the mine sites to the port, from there it's shipped to the market, they lose millions if the trains are stopped. So now this little cabinet houses some equipment called asset protection telemetry devices. What it does is it gathers data from the local sensors, and then it sends, there is an antenna here, up there, above the solar panels, shoots the data to the nearest radio base station, and then it further goes down and all the way ends up in Perth. They have an operations center near the airport terminal 3-4, Qantas, you may have seen. So that's where rooms, I don't know, 10 times bigger than this. They have these big screens, that's where live mine and train data is shown, all the blinking lights, everything obviously has to be green blinking. That's where they do their operations and maintenance. So the feasibility, what's that for? In this case, this is connected by a radio, which are no longer made. So there are no spare parts. What happens when this radio fails? We take one out from the very limited stock that's left. So it's a high risk that eventually we're going to run out. Train's going to stop. We don't want that to happen. So we proposed a few solutions. Eventually, what looked like a good solution, even though expensive, was let's put everything on fiber. It's like, okay, it's only 500 kilometers this way, 500 that way, no problem. We'll do the feasibility. So we did a feasibility. There'll be a mainline fiber parallel to the train track, and we'll decommission all these radios, connect all these little asset protection telemetry sites to the fiber, and then that's it, problem solved for good. He's standing here. This is the closest we can get for a fiber. So this is just an example why we need feasibility. So we need to get to this cabinet. We can dig a trench, put bed and pipe, or we could buy an outdoor rated cable, just bury directly. We could do something called above ground troughing, like a concrete channel. So all these options. This photo just tells you all the different little aspects we do during concept design. So feasibility is done, we tell them, okay, this is how much it's going to cost you, this is how long it's going to take you, and then they make a decision whether a project needs to go ahead or not. In this case, it did. I have a drawing I can show you. Uh-oh. That's open. Okay. All right. Concept design. I didn't add those in the slides because I didn't want it to become too big, and also I didn't want you to have copies of this. It's not confidential. You can see that from Google Earth. So see these little towers? This is where the data is gathered. This little site from this point to this point is 200 kilometers. So this is just like the train network in Perth, we have different lines, Fremantle line, Armadale line. So these are the names of the lines: 7 Mile, Cape Lambert, Paraburdoo, Yandy. These are the main mines where the trains actually gather the iron ore and go all the way to the port. So this is 100 kilometers at this point on. So what we do, the concept design for the IP network looks very simple. This is it. That's it. So it just shows you, see the core switch layer, aggregation layer, and then access switch layer. All of these are just the sites. It doesn't tell you equipment, doesn't assign any IDs or anything, because the concept design, the purpose is not to build, but to estimate cost, estimate time. So this you can just, this is your IP network, all you have to do is count how many sites, how many materials of different types. So I will close these. IT help. So the people online did not see my.
I may not have. I was hoping that they would.
It's all right.
Share.
I've got a question for you. So the problem was the radios are
Obsolete.
obsolete,
Yeah.
and you've got a finite stock that you can restock before
Yes.
they run out.
Yeah.
And the proposal or the feasibility was around a fibre installation.
Yeah.
Was a rebuild of the obsolete radio considered?
Yes, yes. That was one of the options we gave them. None of the data radios were like for like replacement. So it wasn't something that unplug and plug. We had to do the whole wiring, power system and everything. And then none of the major companies that we could find that could guarantee a supply for the next 20 years. So it turns out we could find a good data radio, but we could be at the same stage in 10 years' time. So fiber means for good. Because with fiber, all you have to do is use different transfer receiver, because right now we could be using, say, one fiber core for trans receive. If you use a more expensive, fancy kind of trans receiver, you could use a wavelength multiplexing, one core for multiple signals. So the fiber seems like a permanent, long-term solution, and because it's just a medium technology in the end, you could use a different type of networking devices later on.
Cost-wise, I would have thought
Cost-wise,
the
yeah.
radio would have been way cheaper.
But because the equipment we are replacing were built in, I guess, before any of these were born.
Yeah.
So that means in order to get to that stage where we know, okay, the same problem is happening again, we cannot source more radios, the company shut down. The company doesn't exist,
Sure.
right?
But that's an opportunity for a new startup company from young, bright minds to say, hey, we can rebuild your box at a quarter of the price, at a quarter of the volume, that does the same job.
Time as well. And also they hire subject matter experts, guaranteed solution.
These guys, anything else will guarantee a solution,
Mm-hmm.
and
For
it'll be cheap.
cheap.
Yeah.
We had a sales pitch, but we rejected it. Okay. This is the preliminary design. So the project has been awarded. Your company now, you are one of the system engineers. This room, look around. So there is a wireless access point. There are lights, another wireless access point, ventilation, electrical, sound system. Usually all of these are done by individual different engineers. You're one of them, right? So the preliminary design is first design post-award detailed, but with assumptions. What does that mean? It's a good design, full detail. You can has almost detail to build. But because your design has a lot of dependencies, let's say you are in charge of designing the Wi-Fi network, you need to know the room's layout. But if the designer hasn't even designed the room, how are you to go ahead? So you have to make assumptions. So that's what this design phase is. Very detailed, based on the concept, but with assumptions. So you don't really buy materials at this stage. Only if something is long lead item, you get permission from the customer, then you buy, but usually no. So the most important thing this stage does is set out design criteria and performance criteria to ensure compliance with the requirements. Now requirements, I'm going to assume you've all seen Gemma's lecture. So you have a set of requirements. In your design, preliminary design, you set out something called a design criteria, which is just a guideline of set of rules you follow, which your design complies with. For example, one of my projects in Queensland, Wales, I'm designing the fiber optic network for their rail network. The requirements are thousands of requirements. So the bits and pieces here and there where you gather information, like for example, they would say signaling, all the signaling wayside locations must have at least 4 cores of fiber, but in 2 separate cables. They cannot share. None of the signaling cables could be used for, say, operations network. So all of these scattered requirements here and there. So we gather all of these, and the conclusion is we can fulfill all the requirements with 4 fiber separate cables of 12 core fibers. That's our design criteria, step 1. The train line will have 4 fiber optic cables, at least 12 cores, and then the reviewers will say, okay, hang on, does it comply? And then they go through, yes, actually, it ticks every box. So that's your design criteria example. Performance criteria is, for example, you're building a microwave link, and the customer tells you, and if it's a customer that knows telecom, they will tell you the availability, which means the minimum allowed downtime on a link. So they will tell you performance, we need at least 4 nines. What does that mean? 4 nines means 99.99% availability, which translates to 52.6 minutes per year. That's your performance criteria, that you will design that microwave link so that it does not go down for more than 52.6 minutes in a year. So this is what you put in the performance criteria, design criteria, that goes in your report. Examples of the preliminary design are scope of work, you already know that from requirements. Preliminary design report and calculations, block diagram, which is a big picture, everything. So block diagram of this room will be all the devices. Not devices per se, system head ends, main locations. So one picture, you can see how many systems are there. Then the system architecture, which is per system. So your IT backbone network will have the drawing we saw before, the block diagram sort of, that was an architecture. Then we have layouts, which are something like this. So on the top left, this is the site, the whole rail network. Then we split that based on project management, so delivery stages we call them. Second is the delivery subsystem. Then further down, I think the third sheet is probably 200 to 300 meter resolution. So this is the kind of detail we put in I guess further down will be these little boxes are the cabinets. The cabinet layout, then there's inside the cabinet, you can have cabinet elevation, which equipment goes at which level, and then the equipment has if it has subboards, modules, that layout. So this is the example of preliminary layout. This is design review. Design review, okay, so interdisciplinary review is, I'll give you an example, that'll be easier that way. So let's say as electrical engineer you are to design a power system for a CER, comms equipment room, or CR, comms room. What you do, you're like, yeah, too easy. But then you need to know, okay, what am I designing for? What are the devices I need to power? How many? Where are they? AC, DC, what's the voltage, how much power? All of that is done during the IDC or IDR process. You need to see other engineers' designs. They need to see your design. So once we reach a certain stage, say you are doing a preliminary design, all your documents and your drawings are ready, you then distribute to other engineers. They review it, send back your comments. Some people need to provide services for your system as well. Say for electrical engineers, there'll be infrastructure engineer. They'll say, okay, how many devices you have, how much rack space you need. Then HVAC engineer, the heating, ventilation, AC. They need to know how much heat are you generating, etc. So they need to see your design. So this IDC process happens at every major design release stage. The interesting thing is, it's not only the engineers within your own company. It could be, depends on the, again, complexity of the project. It could be multiple different companies, so you have to deal with them. Your project engineers will get you in touch with them. then it's your interpersonal skills, negotiation skills, you have to deal with them. The thing is, they send you comments, you send them comments. You cannot proceed unless a resolution is achieved. There's a sheet you have to sign. That doesn't mean somebody says, oh, you should move your equipment, and then you have to say yes. So that's where you negotiate. Why? Is there a way, middle ground, etc. So that happens at IDEC. Design review, you probably have that as a milestone in your design as well. Is there design review? Yeah. Design review is when your design is ready to go out to the customer. What happens? There's the next slide. Safety in design can happen in parallel with the design review. This is where the relevant stakeholders gather in a room and go through your design from a construction and maintenance perspective and see if there are any parts of the design that can harm a person or asset. So what we do then is everybody brainstorms, do a risk assessment, we assign some sort of risk rating to that, and then we find a control. Is there something we can do in our design to lower that risk rating or remove it entirely? So that's what we do at SID. Now the design review itself this is a typical design review process. What's happening here, columns are the stakeholders, rows are the review stages. EPC contractor, in this scenario, it's us, design engineers. Principal is, okay, first the company. Company is the company that actually funds, that owns the project, who started all of this. What happens is, even if it's a massive company, let's say Chevron or Rio Tinto, they don't have enough manpower or brain power to manage every aspect of a design. There are thousands and thousands of drawings. They don't have as many resources to check them and ensure they comply. They are even, the designs we're selling them are even legal to build in Australia. So what they do is they hire another company. They are usually called, say, design delivery authority or principal. In a lot of cases, say, you're building an LNG plant. There's not one company in the world who can actually do everything in that massive project. So some big companies, they create something called a joint venture. One company is an expert in building underwater pipelines. Another is good at control systems. They join hands, they deliver a project. They hire subcontractor companies to do, say, electrical, civils, telecoms. So depending on the project, there'll be more or fewer columns. But the principal manages all of those stakeholders for the company. Ivy is the independent verifier. Their job is to verify our work. So they check the contract, they look at our design, they look at Australian standards, and then they see we are complying with the requirements. ISAR, similar, independent safety assessor. What they do is what pretty much Ivy do, but from safety perspective. So you submit, you have a major design submission. Everybody reviews that. This is, so this is the stage, that's design review. A design review workshop happens sometimes in a company, smaller system, you can manage within the company, 20 people. Sometimes we have to book a conference room in a fancy hotel for 2 days to go through the design. So afterwards, we receive an Excel sheet with hundreds of comments. Never it's never happened, any magical design I haven't seen where we have, the design has been accepted during a workshop. So you'll have all these comments. This I've just put as example, T plus 10 days. This is mentioned in the contract, how much time we are allowed at every stage. We're going to just say, here you go, design for review, take your time. Well, if you do that, we cannot control the schedules. So we get the comments, resubmit the design to all, so they do that individually in their own time. Send the comments back to the principal, and they then send it back to us, and then tell us whether our design complies or not. So basically, did we pass or did we fail? So this little diamond shape is a very crucial point in our designs. Obviously, our ideal outcome would be compliant, design approved, done. But it's not easy with bigger projects. This goes on for a long time. And our job is to make the design efficient and compliant as much as possible to limit these revisions. Because, see, all of those people spending time on a review. It's not just you designing, it's the dock controller, it's the CAD people, and then dock controller on the other companies, all these companies, their engineers, their reviewers, all of that. So this is where your design experience, your negotiation skills, your interpersonal skills, all are useful here. So if somebody says, oh, this part of your design is not compliant, you are like, I don't agree because this is a reason it complies. Or somebody says, could you please add another cable? Okay, so it's gonna change my whole design, and my design is compliant based on these requirement number 2500. So this is where you sometimes even, it's not that you don't change, even if your design complies, that's where you find a middle ground. The customer is paying. If they want you to change things, you can change, but you have to also do your own analysis that, is it gonna cost you? You cannot just promise, yes, we'll do that, and then you have to buy more materials. Or it's going to actually increase construction of effort. For example, for this fiber project, the customer asked me, can you use rodent protected cable? I said, okay, I have to look at that. It's not a requirement. Checked that price is almost double. So I couldn't just say, yeah, we could do that, because that doubles our material cost. Now, so what I did was, so we proposed that the middle ground was we included construction in our discussions and proposed sealing for the conduits, some expensive sort of sealing. So that's what was the middle ground. So anyways, your design gets to, sometimes, this is a stage, I have also seen companies involving lawyers. This is where, if you cannot resolve within engineers. Because you read something, people may interpret something differently. You're reading this line and saying, okay, we are complying. They say, no, you're not complying. Your design is approved, let's suppose, your preliminary design. Then next you do detailed design. That again goes through all of that. Once detailed design is done, that's when things get easier. Detailed design. So it's the final design. So you remove all the assumptions that were in the preliminary design. Then you start procuring things, and the examples of the deliverables are safety and design report, which you did in parallel with the design review. Detailed design report, calculations, schematics, cable schedules, layouts, bill of materials, test plan and procedures. Work method statements are just activity procedures. Work method statements is activity by activity procedure. So, say for example in this room, there'll be a work method statement to install access points, which can be used wherever they're installing these access points. This is the IFC. IFC was? Yes, first line, first bullet point. Issued for construction. Your detailed design has been approved. You've reached a major milestone. Your company got paid. Everybody's happy. Now, IFC is easy to achieve. There are almost never any design changes from this detailed design stage to IFC stage. Maybe some cosmetic changes in the drawings, but it's just basically issuing them and they stamp it with IFC and then we get that. For construction, this is the only version we can use. Otherwise, your insurance is not going to cover that construction. So detailed design with IFC stamp. Work pack and control copies are, so when the work is, construction work is split in different milestones. So for this room, they won't bring their whole 10,000 engineering documents. We only issue them whatever is necessary, just enough to build this room, to fit out everything in this room. The test procedures, just that apply to this room. So that's a work pack for every milestone activity. And the controlled copies are necessary because there's this line, it's called red lines. So red lines are the changes that are done in a field. I have examples I will show later. I don't want to disrupt the system now. So your design showed these screens, installing these screens, 200 mil from each side. Construction people call you from site and they're like, Ruby, this is not going to happen because there is a beam, we have to move that. So you do a bit of analysis that how is it going to cost me money? Is it going to change a lot of design drawings? Ultimately, you agree the design goes through a change process, you approve that change. So what they do is on your design, they use a literal red pen, that's why it's called red lines, and then they cross off the dimensions and redo the dimensions. So those, imagine if you were to issue multiple copies of the same drawing, how would you control those copies? So that's why there are controlled copies with sequence number listed. So we can print all you want, but we receive the red lines because engineering receive those red lines. So it's important for us to understand what it means. So the controlled copies are issued and they are used for construction red lines. What you do at that stage, your design is approved, your materials have been purchased, your job is done? No. You do something called project engineering at that stage. Project engineers do construction support. Construction support is basically helping construction understand your designs. You go to site, they bring you drawings. The moment the construction technicians, they see you, they're like, okay, it's easier to ask the engineer than try to make sense of their drawings. So then you get phone calls from site trying to understand what you've drawn because people have different educational backgrounds. So that's where, so you have to be there constantly supporting construction. And it's not just site. So your equipment, say you're building a rack. you have all the drawings, so given them, you purchase all the materials, your company has a warehouse in Perth, that's where everything is built. You go there time to time for inspection, because one is you're curious to see what your design will look like. Then you want to also, for future, you want to improve your design. You see what you could do better. Maybe you could add extra cable management. So these things, so that's inspections. Testing and witnessing, FAT and SAT. FAT is factory acceptance testing, SAT is site acceptance testing. So this is done for subset of equipment. You build a rack, you do a FAT testing, you either test it or some technician tests, and you are one of the witnessing engineers. Usually one or multiple stakeholders, depending on how important that system is. Say for control systems, you'll have multiple engineers coming from all of these companies to witness that test. So rack is built, tested, ships to site. On the site it's fitted out. You get some phone calls, cables are done. You answer your question. You go there to witness a SAT test, site acceptance test. Similar to FAT, equipment based. Say for a radio base station, you will test the transceivers, maximum power, their receive sensitivity, etc. But there is something called commissioning as well. So commissioning is also, some people use that interchangeably, but in my experience, it's like SAT is equipment, testing the equipment, but commissioning is the service, the functionality. So for in case of radio system, you check, can you actually make a phone call? Can you use the radio? What's the signal strength at X point, Y point, Z point? So that's commissioning. So red lines we covered, field change approval. Construction tell you, we cannot install it here because X, Y, Z reason. Okay. That was alarm 45. Okay. So what happens next? Yes. So then construction changes you approve or you reject, and test the final commissioning and handover. So that's the handover of the system. So the unit is being built, but you hand it over this room, and then stage by stage you ultimately hand over the whole system. Next stage is IAB, issued as built. So your design is done, you have built, you have tested, handed over, you've received the red lines. What do you do then? You send that to, first you verify that you've received every red line, controlled copies, easy to track. Your drafting team, then you assign based on the schedule, if it's urgent or whatever, whenever it's assigned. Then the same drawings your design are redrawn, but with the changes that were done in the red lines. And then you stamp that with as built, and the design goes out. That's it. That's your engineering design life cycle in an EPC contract. Additional deliverables are test results, which, FAT, SAT, commissioning. Reports, certificates. So anything that's built in a factory in another country or here comes with the certificate. Any software licenses, you create training manuals as well. Depends on the contract. It's not a fun task, but this is what you have to do in the very end. When the project is finished, the very few engineers that are left, this is what they're doing usually. So something called MDR, manufacturer data report, is it's thousands of pages. It contains data sheets, user manuals, and troubleshooting guides, etc. You don't create those; you just assemble those. but they end up for everything. Everything. There are thousands of documents. In one of my projects, they said, in the contract, they said, we need 2 paper copies, 1 electronic copies. We're like, are you sure? Like, this is a lot of paper. What you gonna do with that? Okay. So at that point, we were, I think, 4 years down the line. Everybody was up to here. Okay, let's just get it over with. We got those printed. We had to hire C containers. I'm like, okay, here are your documents. Where do you want them? That happened. So, and that's it. I can show you first questions, and then we can see my drawings, if you want to. No?
Questions, anyone? Just one question. So you mentioned like IFC and SBOT as well. And this would you be the contractors, and this would be handling like issues for tenders, or would there be other your company, or is your contract?
It depends. It depends which company you work for. Like if you say, if you are working for the parent company, Chevron, when they were doing a tender for their LNG plant, or Rio Tinto when they actually were looking for feasibility studies, then you will create those. But because I guess the number of engineers at the parent company are smaller than at the consultant, at smaller, a little more than at the contractor, more. So, and in fact, even salaries also go in that way as well.
So what I missed on the last slide was support. So when does,
Okay.
what team does the support for?
Good, very good question. This is excluded in the out of scope. This is the
That's not my problem.
this is the out of scope slide. There is something called operations and maintenance at the end, and decommissioning. So I just mentioned a little bit here that this is the longest phase in a project. Once we hand it over, we build you the uni, you use that, right? So somebody maintains this. Either uni's own staff, they have their IT, or maybe they outsource to somebody. So some companies who build, some of my EPC contractors, they have a subsection discipline in the company, sort of like a mini company. They do ops and maintenance. So it makes more sense for the owner to give the ops and maintenance contract to the same company who's built it, because we have, even if engineers move on, you'll still have somebody who works in that, and they can answer some obscure questions.
So your project, which is around fiber, okay, and replacing equipment that was out there 25 years. So that's now in the decommissioning phase.
Yeah.
So what's happening with that? Does that company still exist where you can go back and say, right, we want to decommission this stuff?
No. This becomes part of the proposal in the feed. And then whoever, the company when we build, interestingly my company did that. They were called something else back then, but the engineers who are retiring age, they remember back in my day, we did that. But let's suppose they didn't. It would be in scope of the company who gets to build the fiber. So part of their scope of work would be to decommission the previous radios. Because it's not just a matter of switching it off. You need to see where it's even going.
Yeah.
Yeah.
I mean,
They
so
could.
its whole life cycle, but 25 years ago, I'm not sure they really cared what happened to the equipment at the end of life.
That company